Okay, here we go with geometry lesson on the area of a circle. Here's some nice random circles. This is my little blue bowl that has no clever adjective attached to it like my Hoover Dam mug. And this is just a round coaster that's got, I think it's a hieroglyph on it. But anyway, they're circles. We remember that they're all the same aspect ratio. They're both round. Who'd have thought about that? Okay, finding the area of one of these things. You know, I'm remembering that area is all about unit square, and just offhand I'm not seeing anything square here, so I've got to reduce it in something. Oh look, there's another circle, smaller one. Somehow I've got to make this, I've got to squarify it. It's got to be squared somehow, because I've got to have little squares, or I can't count my little squares and then I can't have my area, because all area is unit squares. Okay, well here I've drawn myself a circle and I sliced and diced it to get some unit squares. As I look at that, I say, well, I have some squares here that are completely inside the circle. So those are part of the area of the circle itself. Then I've got a whole bunch of other squares out here that part of it's in the circle and part of it's not. So I'd have the part here. So there's the red that's inside. Okay, so I know that the area of the circle is more than 4 units, because these 4 red square units fit in there. Okay, well what if I look at all the rest of them? Okay, so I'd have here, like this, all the way around, 1, 2, 3. See this big rectangle, there's a square actually, composed of these smaller unit squares. I'm now sure that that's bigger than the circle. So now I know that the area of the circle is smaller than 16 square units. Does everybody see that? Okay, that's not narrowing it down very much. Well, let's see. What if I do it again? What if I make another slice in between each one of those? And I do the same thing. Okay, so then I'm going to have the ones that fit in. Well, not quite. So what am I doing here? I'm coloring, oh, not that one. The ones that are exactly inside. So that's 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5, 6. The way it's situated in here, is that right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So that's 30 in the middle. And 31, 32, 33, 35, 36, 37, 38, 39. That's wrong. I counted it wrong. 30 and 8 is 38. Sorry about that. Okay, so the red area there, I know the area of this circle, which is the same size as the other one, is bigger than 30 of these smaller square units, and it's going to be less than, let me see how many got part of it. Yeah, right there. Yeah, that one's got a little piece right there. Ooh, that one should have been all the way in. Sorry about that. Isn't exactly centered, and I was kind of assuming it was. So this one, all of these. So what I'm doing here is I'm coloring in the squares that have some portion of the circle in it. So that was my 31, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 1, 2, 3, 4, 5, 6. And so now I know that it's less than 56 of these smaller units, which are 4 times as big as the other ones. So I'm narrowing it in a little bit. Notice that the range is now a little bit better. If I just keep slicing and dicing and more and more, put a zillion little lines in between, then eventually we're going to come really close to what the circle is. let's look at another way of thinking about what we're doing here. Okay? That's one way to think, and it's going to converge on the number that you know. Well, let's look right here. If I take my circle and my grid and I put it into, so that's how, the one that I just did is how it's really done. And you'll do that in calculus. You'll probably maybe even actually have a proof to prove what that pi r squared is the area of a circle. Here I've got one that's the same. I just kind of intuitively want to look at what we're doing here. Okay? So if we have, let's look. I have 4 sectors here. If I look at one particular sector that encloses a circle, now I'm not using sector in the circle sense, just as in area portion of it. This is the radius of the circle, this is the radius of the circle, and so this is radius squared. So this here is radius squared, the whole thing. But look, there's this piece that we don't want out of radius squared. So this would be a whole 3, a whole r squared, then a whole r squared over here. Do the same thing for the whole thing, but this piece left over. And then here another whole r squared, but this piece left over. So what that would look like with the leftover pieces, and where did I put my scissors? With the leftover pieces, okay? Let's see just how big those leftover pieces are not. So I've got one that's the same, see it's the same, and I'm just going to cut out the leftover pieces. Okay, there's one. And there's one. And there's one. Okay. And I'm looking over here at this other sector that I hadn't counted yet. I cleverly know that pi is 3.14, so I know it's probably going to be 3 whole squares and a part of another one. So here's another one. There's 1 whole, 2 whole, 3 whole, and part of another one. So when I take this and I slide it over here, okay, I'm going to try and fill this thing up. And then I stick another one in here. Okay. It's not real obvious, but if you think about it a minute, that's going to turn out to be about 1/7 of it. You start, yeah, it's my crude drawing, but it's about 1/7 is how much it'll be. So this is not a proof in any way. It's just kind of to try to give you an idea that it actually does work out. Here we have our typical, everything's got to be a square because it's area. We have 3 complete squares. Okay. And how much does it take to fill it up? Okay. What it'll turn out to be is 3 1/7, because the part that you want is the part I hadn't got it to yet. The part that's down in here, how much is it going to take to fill it up? Okay. It's about 3.14 r squareds. Okay. That's where it comes from, and again, that's just seat of the pants. It's not really anything official. Okay. So now, let's talk about a for real sector. We've defined it before that the term of art in math, in circles, called a sector, is defined as the area enclosed by 2 radii in the intercepted arc. We've had that definition before. Now, along with the way that we just did in the previous lesson, we're going to see that there's a relationship. Before we saw there was a relationship between the length of the arc and the whole circumference. Now we're going to talk about the relationship between the piece of pi and the whole pi, or the area of the sector and the area of the entire circle. Now, of course, we all know that the area of the entire circle is pi r squared. And we know from the similar argument to the one made previously in the unit before this one, it's all going to be proportional. If this is a 60-degree angle, which it's not, if this is a 120-degree angle maybe, then this is 1/3 of the whole pi. And that's going to go both for the measure of the arc and the area of the sector. It'll come out to have the same relationship. It's 1/4 of the pi, it's 1/4 of the degrees. Okay? So, this one, we've simplified it. It's just basically solved the proportion. You can do it this way or this way. Truth be told, I personally don't learn this one. I just always set up proportion. It's easier for me. It's which way you'd rather have it. This has it isolated. If you're looking for the sector's already isolated, it might be easier to put it into the calculator. Again, when you're setting up a proportion, you're going to be comparing the part to the whole circle, the part to the whole, and the area to the measurement of the arc. Okay. Let's look at a few of these. Okay, here, let's look at problem 26. Okay, look at that just a moment. We'll see how that goes. Try to find out, try to figure out right there, problem 26. Take a moment and then I'll show you how I've done it. Okay, here's what I have. Okay, what did I do? I found, I recognized that I needed to find the area of the entire circle and subtract out the triangle. So from that, I needed to be able to find the the radius or the diameter of the circle, and to be able to find the area, and then the area of the two triangles. I did the triangle first. We know that it's a special right triangle. It's an isosceles right triangle because the two legs are radii. So we can use our handy-dandy shortcuts and find out that the radius is 5 over the square root of 2. Having done that, we can find the area of the circle by squaring it, multiplying it by pi. Keep it in terms of pi, it's usually easier. And here's the area of the triangle, because we now have the base and the height, and we need 2 of them. We figure it on out here, and here's where we subtract. Okay, that's number 26. Also, now if you would look at number 30. Oops, here we go. Number 30, not that that's going to hurt you. Pause it, and then here's how I did it. I calculated the radius based on each individual section being 1, so the radii are 2, 4, 6, and 8, adding 2 each time. I just went ahead and multiplied it out and added it. Okay? So, there we have number 30, and here's the rest of them. As you just saw, go ahead and work them. And I'll move the answers up. I'll make them a little bit bigger, then I'll move the answers up so that you can see them. Okay, when you get ready for them, here are the answers. Okay. Now here's a fun thing. Give this one a go. Let's see. Yeah, okay, there we are. In the diagram, circle Q and circle P are tangent, right here. P lies, the point P lies on circle Q, making that a radius, The measure of Rx is 108. Find the area of the red region, the area of the blue region, the area of the yellow region. Leave your answer in terms of pi. Okay, pause it and give that a go. And here are the areas for you, the answers. Okay. Here's some fun ones if you want to play with them. Okay. Oops. There we go. And here endeth the lesson.